restaurant and come home. You're not my real mom.
Oh, goodness. And I did go ahead and post that to the Twitter feed. So,
That's fun.
yeah, I like that one. All right, so how much does an atom weigh? Well, we kind of got an idea how small it is, so we're not going to talk about its weight in pounds or grams or kilograms or anything like that. We're actually going to introduce a new unit of mass called an AMU, atomic mass unit. Okay. So AMU stands for, atomic mass unit. So let me pull up my thing here. So it's just another measurement of mass. What I was going to mention is that I learned it as AMUs. Honestly, it seems like some of the textbooks I'm using for my general chemistry, now instead of an AMU, they will actually use the symbol U for an atomic mass unit. So just so as you know. How much does an atom weigh? We can call that the average atomic mass, we can call that the atomic weight, or we can call that the atomic mass. It's all the same thing. How much does an atom weigh? See the word atom in all those. We're actually going to talk about how you get to how much an atom weighs. By the way, let me go ahead and now, instead of every box, usually for an element, has a whole number. The whole number is the number of protons. The decimal number is this. Decimal, you'll hear me call it the decimal number, okay, is how much an atom of that type of element weighs. And if we pick on some of them, you might even come to memorize not even just the name and the symbol, but its number of protons, its atomic number, and its average atomic weight. But if you look at carbon, carbon's decimal number is 12.01. Hydrogen's decimal number is 1.008. What does that mean? It means that a carbon atom weighs 12.01 AMUs. It means a hydrogen atom weighs, on average, 1.008 AMUs. Do you need to memorize those? No. But we just do a lot of calculations with carbon and hydrogen, so you might eventually. But the decimal number is how much it weighs in AMUs. That's my point. And we talked on Friday this idea that of isotopes. We said that, it's possible that you have two carbon atoms, for example, and one has some certain number of neutrons, another has a different number of neutrons. The atomic number for carbon is 6, so it's got to have 6 protons, but the number of neutrons, okay? You change the number of neutrons, you change the mass. So actually today we're going to do a very standard calculation in chemistry, that is to look at the isotopes that you have for a given element and come up with what's called a weighted average. Okay. We're actually going to come up with those decimal numbers based upon the isotopes that are out there for a given element. Okay, I'm going to show you how you do that. And actually in lab on Thursday we're going to get some more practice at that. So an AMU, sometimes called just a U, AMU stands for atomic mass unit. And we always have to be able to, let's see, how do I say this? We always need to go back to some standard. And the standard actually is carbon. So basically the standard is if you were to have one carbon atom, and I can chase this down if you're interested kind of outside of class, but one carbon atom, notice which isotope it is. We talked about how you can tell which isotope you have by putting the mass number. This is mass number 12. Okay, so it has 6 protons. How many neutrons does it have? 6, exactly. So we're talking about that particular isotopic form of carbon. One carbon atom would weigh exactly 12.0000 AMUs. That's the standard. Okay. So, but you might need to kind of scale up an atomic mass unit to something a little more tangible, like grams. So I have 2 equivalency statements. They are the same, okay, and there is uncertainty in them. One AMU is approximately equal to 1.661 times 10 to the negative 24th grams. If you take 1 over 1.66 times 10 to the negative 24th, actually you get this other number down here. 1 gram is approximately equal to 6.022 times 10 to the 23rd AMUs. I hope that makes sense because an AMU is really small compared to a gram. Some of you guys might recognize that 6.022 times 10 to the 23rd. Some of you may even have a t-shirt with Avogadro's number on it. That's what that is. That, yeah. Avogadro's number. And that's not a coincidence. It's an interesting thing to kind of chase that down, why that is. And actually, in the next part, we're going to talk about Avogadro's number. Okay, so when we talk about how massive an atom is, we need to switch to AMUs, and that's what that decimal number is. The average atomic weight in AMUs. So before we're kind of building up to coming up with those average atomic weights for an element, and we talked about the fact that some elements are only present in one isotopic form, which seems kind of strange to me. Even more, though, have 2 or more different forms. They can have different number of neutrons in their nuclei. So in order to do this calculation I'm going to show you, we need to know how much there is of each isotope. That's what percent abundance is. Okay? Percent abundance talks about how much there is of each isotope. So basically what they do, and it's this whole idea of sampling is a science in and of itself, but they get a representative sample of, for instance, all the carbon atoms in the world.
It's a lot.
You're like, yeah, I don't know how they do that. But once they get them, basically, they count the number of carbon atoms, okay, the total number of carbon atoms of all the isotopes. They put it in the bottom. Then what they do in the top is they put how many were a particular isotope. So basically, it's a mixture, right? They're basically coming up with the percent of one isotope in the mixture. So then to get it parts per 100, they take it times 100. Okay. So whenever I'm going to show you some data where they went and looked at different forms, different isotopic forms, and you're going to see these percent abundance numbers, and that's how they got them. Okay. So for instance, if we pick on copper. And we said one way to talk about the different isotopes, or one form, is basically to put the mass number in the upper left-hand corner. Okay? So here we have copper and copper, and I'm going to walk over here. Copper is atomic number 29. So 63 minus 29 is
34.
34, I'm liking that. 34. So do you buy this, that they both have... what did I say, 20, dang it. They both have 29 protons, but the first one has 64 neutrons, all right? And the other one has,
You mean 34.
sorry, 34 neutrons, and the other one has 35 neutrons. Yeah.
There's 2 more on that one, right? No, because there's...
You're right, 2 more, 36, perfect, thanks. So, very good. So this one has 29 protons, and 63 minus 29, it has 34 neutrons, perfect. And this one has also 29 protons, and it has 2 more, yep, 36 neutrons. Do you buy that? Okay. So we're picking on copper for actually a couple of thoughts here. So they went out and they said that, notice the one that's more abundant is the lighter one, right? Okay. What this means, and don't get too hung up on this, is this the percent of about 70-30, or more precisely 69.09% versus 30.31%. That means if you move the decimal place over a couple places, if you had 10,000 if you had 10,000 copper atoms, 6,909 of them would be the lighter one, 3,091 of them would be the heavier one. Okay, so we're on about a 70-30. Cool. So that's what that percent abundance means. So here we're picking on neon, the 3 isotopic forms of neon. By the way, the 3 isotopic forms of neon, if I go over here to this last column, what should their percent abundances add up to be equal to?
100.
100, that's right. Now, sometimes students will ask me to work a problem like I'm going to show you. Do I have to calculate this? No, this is the data that will be given to you in this case. Okay? So yeah, neon is atomic number 10. So notice that each of them have 10 protons in their nuclei. With regard to neutrons, we have increasing number of neutrons, 10, 11, and 12. The mass number is always the number of protons plus the number of neutrons. So that's where that third column comes from. So here are some other elements. Okay, we kind of draw kind of a line. Here we have hydrogen, 3 isotopic forms of hydrogen, 2 of boron, 3 of neon we just saw, and down here we have the isotopic information for the element magnesium. Okay. If you've ever heard of heavy water basically is water that has, instead of H, has 2 hydrogens. Well, it has 2 hydrogens. But heavy water actually, instead of normal hydrogen, it has heavy hydrogen. Sometimes heavy hydrogen, it's called deuterium, and sometimes it's represented with the symbol D for deuterium. Okay, heavy water. But we are going to actually come back to hydrogen, check out the abundance check out how much Mother Nature says deuterium is present. We're like, dang, 0.015%. And that actually, deuterium's kind of been in the news. If I remember it right, on the moon, actually, there's more deuterium than there is here on Earth. Okay, and actually, the amount of deuterium is actually a player when you're looking at kind of the evolution of our universe. So it's kind of an interesting thing. So anyway, yeah, so kind of keep that in mind. Heavy water, by the way, before I leave it, if you're like, I've heard of that somewhere. Well, you may have heard of it when it comes time for nuclear reactors. For some reason, heavy water is a better fluid to have in your reactors.
Or I think the coolant.
Yeah, I think so too. To cool the cores or the rods. I don't
Yeah.
know. Where's Homer Simpson when you need him?
Right.
Okay, so we're picking on copper. Copper has 2 isotopic forms, and we looked at their percent abundances a minute ago. Now down here, what we're also going to need to know is how much does a copper atom of these different isotopes, we would call this copper 63 because it has a mass number 63, copper 65. If you look at an atom of each of those atoms, how much do they weigh? So not so surprising, the light one weighs 62.930 AMUs. The heavier one weighs 64.928 AMUs, right? Okay. So you're like, I didn't think this was a math class. But anytime you see this symbol, actually this is a capital sigma, like as in Greek. And what this means is summation. So it means a lot of adding. Basically, terms are added together. That's what summation means. So the things we're going to add together is for each isotope. Remember I told you you're going to be given this. And we actually know this for copper now. For each isotope, you're going to take how much it weighs, that's the first term, times its fractional abundance. And I'll tell you how to get to fractional abundance from percent abundance here in a minute. Okay, so for each isotope. So when we do copper here in a minute, basically we're going to have what we call 2 terms. We're going to have the product, which is the multiplication for the first isotope, plus the multiplication for the second isotope. I'll show you what that looks like. Okay, so summation basically means that you keep repeating this process. If you had 5 isotopic forms, you'd have to have 5 terms basically added together. Okay. So you look at the first isotope, you take its weight times its fractional abundance, plus, if there's a second one, well, I guess there would have to be a second one, otherwise you wouldn't have to be doing this, plus the second one, how much it weighs and its fractional abundance, if there's a third one, okay, plus how much it weighs, plus its fractional abundance, etc. Okay. So again, you're going to have some homework, and then actually we're going to hit this in last too. But they're not bad. I'll kind of show you what it looks like. So one of the things you need to be able to do, though, is to take, for copper a little bit ago, remember I said 70%, 30%? Okay. You're going to have to be able to take those percent abundances and basically make them into fractional abundances. And this is what you do. You take the percent abundance, which you're always given for how much there is of each isotope, and you divide it by 100. So it's not too bad. All right, so here we go. So this would be the stuff that you're given, and actually for your homework that's going to be due on Wednesday, what I encourage students to do is kind of make a little table like this because you'll be given in paragraph form the information about the element of interest. You'll be given in paragraph form what its percent abundance is and how much each one weighs. And to me, I get kind of lost. Sometimes I'll go ahead and add to this. Sometimes I go ahead and add one more column to this, and I go ahead and basically take this percent abundance and I put it into fractional abundance, fract abundance. And I'm all about showing your work. But honestly, this is one time where if you just move the decimal place over, divide by 100, I'm fine with that. Yeah, I actually would be okay with that. So here in a minute, what we could have done, just instead of dividing this by 100, like I'm going to show you, I could have moved the decimal place over 2 places. So that would have been 0.6909, right? Move it 2 places, 0.3091. I could have done that. All right, so let's go ahead and apply that summation thing that you saw before for copper based upon this. So we turn our attention to the first isotope. And this is why I like to kind of pull it out and put it in a little table, because sometimes I read those paragraphs and I'm like, what? Okay, so a table helps me. For the first isotope, we know it weighs in AMUs, that lighter one weighs 62.930 AMUs. Its percent abundance was 69.09, so we can get it to the fractional abundance by taking 69.09 divided by 100. So ready to apply the sigma or the summation part. We're only going to have 2 terms because there's only 2 isotopic forms. So turning our attention to the heavier one, the mass of the heavier one was 64.928 AMUs, and its percent abundance was 30.91. So to get it to fractional abundance, we can divide that by 100. And you need to be a little careful with orders of operation in your calculator. If you do go ahead and instead of for these terms, instead of their percent abundances, go ahead and put in the 0.6909 and, 0.3091. If you go ahead and put those in, it makes it easier. I hear those calculators roaring. This is one of the few, I guess there's a few of them, problems that you can check. How could we check our answer? Assuming that the data is not bogus, assuming that really there are only 2 isotopic forms, this is how much they weigh, and this is the percent abundance. Where else should we see this number? On the periodic table. Exactly. Exactly. So 63.55, and the units are AMUs. So you can check your answer.
So you just round it to...
That's a good point. You round it to, if it's heavy like this, if it's...
I got like 63.5475818.
Yeah. 2 decimals for this sort of problem. And I think I have a slide later
Hey, sweet.
on. Isn't that fun?
63.55.
Go with 2 decimals. I will say unless unless it's less than 10 AMUs. So for the lighter ones, you really need to give it 3 decimals. And this is unusual in that I'm telling you how to round. Usually I'm like, oh, we'll use the rules we talked about. Now I'm kind of like, no, just 2 decimals. Okay? Yeah, so you can always check these answers. And I hesitate to say this, so I'm going to use my quiet voice. Notice what you did not do. You did not take the maths of each of them, add them together, and divide by 2. That would be a simple average. Okay? The reason you couldn't do that because one was present 70% and one was present at about 30%. This is called a weighted average. Okay? So you don't have to write down all this, but this is how this works. Same number. All right. So this is my point about the weighted average. Okay? Oh, by the way, see if this is an important distinction. This 63 and this 65, those are mass numbers. And what we talked about on Friday, they always will always be integers. Whole numbers, how's that? Okay. Mass numbers will always be whole numbers. Why? Because by definition, you are counting protons and neutrons in the nucleus. You can't have a part of a proton, a part of a neutron. Now, I mention that because the mass numbers actually can be used to approximate, and I think I had a slide earlier. You can use those mass numbers to approximate how much they weigh. Okay? So with a mass number of 63, it's going to weigh approximately 63 AMUs. Mass number 65 is going to weigh approximately 65 AMUs. The mass itself, though, is definitely not an integer. Okay, so a simple average, what this slide emphasizes is simple average. If you add 63 plus 65 and divide by 2, you get 64. That's a simple average. But like we know, the periodic table says that actually it veers towards this lighter isotope, right? Because it was present at 70% versus 30%. And another good example is if we pick on hydrogen, remember how much of deuterium there is? It's like 0.0015 or whatever percent. So if we look at deuterium, which is a mass number, or excuse me, a weight of about 2 AMUs versus regular hydrogen weighs about 1 AMU. You add them together and divide by 2, you get 1.5. A decimal number that you might end up committing to memory was that one I told you a minute ago. For hydrogen, it weighs using a weighted average, and now you know where that weighted average comes from. Basically, they have to sample all the hydrogen atoms and come up with relative percents and how much each isotope weighs. So actually, the decimal number we're going to use is about 1.008. All right, so I added this LOL, must show your work, because you know what? These I'm going to show you are, one of them anyway, the last one, is coming up with an average atomic weight for an element. And if you didn't have to show your work, you just go to the periodic table and write it down. So this is what that looks like. So 95, 96, 97. So the first two are kind of back to what we talked about on Monday a little bit. I know, it's Monday. Okay, so 95, talking about carbon, and basically says that if you read all the blah, 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 the bottom line is determine the number of protons and neutrons on a carbon atom that has a mass number of 14. Okay, for the periodic table, its whole number, its atomic number is 6, so I think you'll do just fine with that. 96, again, instead of carbon, it's plutonium. Remember, if they only give one number, that's the mass number for that isotope. And this one, they want you to, oh yeah, both of them. That's what I messed up on Friday. In both cases, they want you to do the whole, where you put the symbol of the name, symbol of the element replace it for X. And then the big number, which is your atomic number, goes in the upper left-hand corner, and the big number, which is your mass number, goes up in the upper left-hand corner, and the smaller number, your atomic number, goes in the lower left-hand corner. So this is kind of like what you're handing in today for your homework. So down to this one, 97, is finally what we just talked about this morning. And this is where I would kind of lift those percents and those weights and put them in a table form if you want to, because otherwise I just get so confused. Basically, rubidium has 2 naturally occurring isotopes. Rubidium with a mass number of 85, rubidium with a mass number of 87. And it's just like we did with copper. They give how much each isotope weighs and its percent abundance. Okay. Again, you can check the average atomic weight of rubidium from the periodic table. Okay? So I do want to go ahead and start in on moles. It makes me giggle.
At least the last slide.
Oh, yeah, so just ignore those slides.
Moles.
The mole.
It's mole.
Yeah. So part of the reason I showed you that little video on how small atoms are is to give you a sense, if somebody's talking about, oh, I got a dozen atoms here, you're like, dude, that's not much at all. So kind of along those lines, we had to, in chemistry, they had to, somebody before me obviously, come up with this idea of, if you want to have something you can sink your teeth into, what is that going to be? Some number. So in chemistry, actually, that's why we have the mole. Okay? So if you have 6.022 times 10 to the 23rd atoms, something you can sink your teeth into. Now remember what that means is if I were to draw that over here, okay, I'm going to move the decimal over 23 places. So 6022, so there's my 3 places. I need 20 places. That's a big number, okay? With an implied decimal right there. That is a big number, 6.022 times the 10 to the 23rd. Just to kind of give you a sense of it, in your remember your 10 mil graduated cylinders in the lab? Okay, how do we go? Is this right? No, I have to say, you'd have to go to your 50 mil graduated cylinder. If you get 20 milliliters of water, which is maybe about the size of 2 of my thumbs, 20 milliliters of water, that is this number of water molecules in there. About 2 thumbs full of water. Okay, so 6.022 times 10 to the 23rd. It's a big number.
How many are in the ocean?
What's that? How many years?
How many are in the ocean?
I don't know. I think, to kind of answer your question, have you ever heard this? That there are more, no, this isn't going to work, but there are more stars in our universe than there are grains of sand on the beaches. I guess that doesn't work for the mole. But. So that's Avogadro's number. So do you guys remember? See, how does this work? 1 gram is approximately equal to how many AMUs?
6.022.
6.022 times 10 to the 23rd.
Yeah.
Yes, AMUs, yes. Very good. And this is one of my favorite abbreviations. You get to drop the E. Yeah, M-O-L-E. You get to drop it to M-O-L. Isn't that not adorable? So I kind of mentioned why we have it in chemistry. You could talk about a dozen atoms, that's fine, that'd be 12. You could talk about a gross of atoms, that's 144. Okay. And actually, I'm gonna kind of switch gears just to kind of show you how big this number is, and not talk about atoms, but I want to talk about other things, including grains of rice and basketballs and marshmallows. Okay. So, rice. So I have here, just so we're kind of, they're not hydrated or anything, but this is 10 grains okay, and this is 100 grains of rice. Okay, bumping it up a factor of 10, okay, this is 1,000 grains of rice. I didn't count these, I just kind of did a density sort of thing. So I'll pass these around. So here are some things about rice. First off, if you had a mole of rice grains, that would be problematic because all of the land areas on Earth would be covered in a depth up to 75 meters. So a mole of rice grains. That is a lot of rice. Again, if you had a mole of rice grains, that would be problematic, again, because even though a lot of people eat rice as a staple in their diet, there hasn't been that many rice grains grown since civilization.
Yep, that's rice.
Again, with the rice grains, right? If you had a mole of rice grains and you were trying to package it up, and you're going to put it in a cube, that cube would be 120 miles by 120 miles by 120 miles. Again, problematic.
This is like a tongue twister. 1 mole of rice grains is more grains than the number of grains of all grains grown since the beginning of time.
It is like a tongue twister. And I think most of these came off of the internet, so you know the internet's right. But some of you can actually calculate using factor label. And so switching gears from grains of rice to marshmallows, that would be problematic because just confined to the United States, we'd be in marshmallows 600 miles deep. Like, why would you do that?
Marshmallow covered America. I'm okay with it.
Yeah.
We'll never find the Michelin Man.
I will eat my way out.
Snowflakes, again, problematic if you were confining those snowflakes to the United States. Now, the problem I have with this is that snow...
I can bring it to you.
Thanks.
Need some work home time anyways.
Snow is sometimes it's fluffy, sometimes it's dense, but I guess so. Again, confining to the United States, it would be up to a depth of 1,000 meters, or 2/3 of a mile.
It's like the East Coast.
Yeah. So here's one, and we're going to talk about counting a little bit. So if you're like, okay, I'm going to pay you or whatever to count, okay? And we want to add these, we're going to have multiple people counting, and we're going to add them all up to be equal to a mole. Well, you could have, at the time this was written, all the people on Earth counting, okay? But you would need to have the people on Earth times 51,000, okay? And they would have to count for 75 years, going Mississippi 1, Mississippi 2, okay? So it's a big number. It's problematic. And again, at the time that this was written, if we take a fast computer that actually could do, instead of taking 1 second to do this, it could actually do millions of instructions per second. Okay, MIP. Okay. Well, a fast computer like that, if you're like, and I don't know if you've done much with programming. I haven't done much with programming. One of the things they always teach you how to do is like this loop. You send it in a loop to basically count, going that fast. It would take 1.9 million years for that computer to crunch that number. That would be cruel. Yes.
How's the computer holding up? Still counting.
I know.
Still going.
Switching objects now to hockey pucks. You could go ahead, if you were able to get a bowl of hockey pucks, that would be equal mass to the moon. And switching now to basketballs, if you were able to gather that many basketballs, a mole of basketballs, it would be equal in volume to the Earth. So not a good idea.
Moles are fun.
Moles are fun. And the last one, if you're like me, you see a penny and you're like, whatever, you know, so I'm not going to even bend over for that penny. Unless it's heads up, then I might do that. Okay, so if you had a mole of pennies, you could go ahead and distribute that wealth. At the time this was written, every person on Earth, you could go ahead and divide it evenly. Every person would get 1.5 times 10 to the 14th pennies. I don't know what that would do to the economy, right?
How much money is that?
Well, if you move the decimal over 2 places, that'd
That's a
be
lot of
1.5 times 10 to the 12th dollars. Does that seem right?
Yeah, it's a lot of money.
That's a lot of money.
Personal spending at the rate of $1 million a day.
So like I'm just gonna draw up a contract on somebody and then like make a wager with them and then win, and I'll put it in moles though. So like
Yeah. Put your
amount of
units in
money.
moles. Yeah, definitely.
It would take 4,000 years for everyone
Yep.
to run out of money.
Yep. I don't know what sort of economy the world would look like, but I kind of
Oh.
like it.
You have to spend $1 million a day.
But here's the problem, just having that mole of pennies, I can almost smell the copper, right? That would be problematic, because again, it's like one of those genie things, never wish for a mole of pennies, right? Because the land portion of Earth would be covered in the depth of 420 meters. So, it's a lot, it's a
Got
big
stacks.
number.
Stacks on stacks.
So we're gonna do a calculation in a minute, okay? So this is an equivalency statement, and we're gonna start with atoms, not hockey pucks, not a mole of hockey pucks, not a mole of rice grains, not a mole of basketballs, but a mole of atoms, which is kind of what it was built for. So 1 mole of atoms is equal to 6.022 times 10 to the 23rd atoms. That's an equivalency statement. We talked in Unit 1 where you can take an equivalency statement and basically make a ratio out of it. Remember, you divide both sides by the same thing, and basically you get 1 on one side, the number 1, and you get the ratio on the other side. So we can take these ratios and insert them into our problem, just willy-nilly, to basically go back and forth between atoms and moles of atoms. Okay, so let's do 2 problems. Okay, the first one is how many moles is in 1 trillion hydrogen atoms? And I kind of finally, just this semester, beefed it up, because 1 trillion, what do you need? Is there any uncertainty in that number? Well, I went ahead and said, what if it's 1.00 times 10 to the 12th atoms? That's 1 trillion. Okay. And then the second one, so that would be going from what? Atoms to moles. The other one is how many atoms is there in 0.555 moles of atoms. So we've done kind of the diagramming thing in here before. I want to go ahead and just show you kind of the strategy. Okay, so basically it says how many moles. So for the first one, it's going to go arrow moles. How many moles, M-O-L-E, is 1 trillion hydrogen atoms. So basically the number over here on the left is 1.000 times 10 to the 12th atoms. And I'll just go ahead and over the arrow write that equivalency statement you saw before. So 1 mole of atoms is equal to 6.022 times 10 to the 23rd atoms. We can do that. And then the second one, okay, again, you can go ahead and it says how many atoms. So actually, if you want to do it this way, I'm going to end up with atoms. So that's my goal, okay, is 0.555 moles. What's that? And I'm just going to go ahead and take that equivalency statement and write it down there.
Is number 2 like 1.08 times 10 to the 24th atoms?
It might be. Does it seem right? It sounds familiar. So here's what these look like then. The first term is going to be the thing you want to convert. So we're going to convert atoms to moles. And I would put that number over 1. I don't have it in my answer key, but I would put that number over 1. So what is the ratio going to look like? What's going to be in the top for the ratio that goes right here? We're trying to go to moles from atoms.
It would be 1 mole. It would be 1 mole over 6.
It would be 1 mole over 6.022 times 10 to the 23rd atoms. Yep. Exactly.
This would be a gigantic, massive number.
And this is where you need to kind of brush off. We talked about never use your 10 to the x key in working these. Always find your EXP or SCI or EE key. So is this, and round it to how many significant figures? Hold up fingers. 4.
4?
Why is it 4?
Oh, because the sig thing, okay, yeah, I was thinking
Yep.
of the, what we're supposed to, like what you said earlier, with the amount of decimals or whatever.
Yep, it is 4. Very good. So did y'all get this? 1, 2, 3, 4. 1, 2, 3, 4. Yep.
So I guess I missed out on like how you get the 1.000 times 10 to the 12th page atoms. Like,
That was given in the problem.
It
That
is?
was the 1 trillion.
how many moles of atoms is 1 trillion hydrogen? Okay, so that's 1 trillion. Okay, good.
Yeah, good. So the next one, the first term's going to be the thing we want to convert over 1. And in this case, we're going to use the inverse, right? In this case, we want moles to cancel. We want to be left with atoms. So how many sig figs are we going to round this one to? Fingers, please.
3.
Yeah, 3.
That was in your fingers.
Oh.
I'm liking it, 3. Very good.
My fingers talk. Yeah, that's what I thought.
Yeah, I wasn't right.
That is a huge number.
3.34 times 10 to the 23rd atoms. Oh, pretty big. So again, and my builds kind of get lost, but I would put that first term over 1 in both cases. Yeah, the first one is what we call an atom to mole conversion, and the other one is a mole to atom, yeah.
I want to get a pet mole and name it Avogadro. That would be awesome.
Any questions about this? Because you're going to have some practice at this.
Because assignments.
Yeah.
But we didn't get to this one, and it's 10, we don't have time to do it. We didn't get to the slide before it, so we can't do it.
She's got
So
it.
it is not 10:50 yet.
10:49.
So these,
We still haven't gone on the slide yet.
I don't think there's a whole lot necessarily to show you.
Alright, that's gonna suck.
Let's take a look at them right quick.
We'll do that.
But these will look familiar. What numbers were they in 6?
19 and 20.
Thank you.
Yep.
Because this is good, I'm glad, because, let's see, next time we meet on Wednesday, this is good to get these separate from the other problems I'm gonna start in on Wednesday. These have your best chance of doing well. So 19 is basically, like the second problem we did. How many atoms are there in each one of these moles? Okay, that's like the second problem we did. You have to use factor label. Notice the answers are in the back of the book. Over here, how many moles are there in each number of atoms? So that's like the first one we did. Factor label. So it's going to be one term, a ratio, and the answer.
I love the factor label.
Okay? All right. See you Wednesday.
Hopefully I'll have my glasses by then and I'll be able to see.
Uh-oh. Watch out.